I will start from the background part. So atherosclerosis actually is the main foundation cause of the cardiovascular disease, which affect around 500 million people and cause around 32% of all deaths globally. And with the development of the atherosclerosis, it actually will block the blood flow in our heart. So due to the lack of the blood, actually there are a lot of disease will happen, something like heart failure, myocardial infarction, and heart attack. And even though the medication can relieve some early symptoms of this disease, but most of patients is detected at a later stage. In that case, the surgery treatment is required. So the most two common surgery to treat this one is CABG and PCI. So the CABG is actually the coronary artery bypass surgery, which uses the artery to bypass the blocked coronary artery. And the PCI is percutaneously coronary intervention, which uses the stent to open up the blood vessel. And due to the less invasive of the PCI, actually is more commonly used in the real condition. And in PCI procedure, stent is used to keep the blood vessel open. So stent is actually a receiving tube that combined with the balloon catheters, which insert to our heart. And after the balloon catheter expansion, our stent will remain inside the blood vessel to keep the blood vessel open to restore the blood flow. And even though the stent have development for many years to improve its performance, but still there is a lot of complications may happen, like stent fracture, thrombosis, and in-stent restenosis. And of all of these, in-stent restenosis is the most common happen. There are around up to 20% chance that will happen the in-stent restenosis, what we call it ISR. So to diagnose this in-stent restenosis, some traditional methods have been developed, like conventional angiography, intravascular ultrasound, and optical coherent tomography. But all of these traditional methods require patients to visit hospital regularly to conduct some invasive tests. And if the patients not so regularly go to the hospital, they will detect the in-stent restenosis in later stage. So to overcome this limitation, the concept of smart stent has been proposed. Actually, smart stent is a concept that combines one sensor with a stent to consist of some smart stent system. So the combined sensor make it possible to real-time monitoring the condition of our blood vessel, and no need to so much invasive tests anymore. And due to the long-term data collection, make it possible to detect the in-stent restenosis in the early stage. So the main principle of the sensor smart stent is actually to detect the pressure change in the blood vessel to detect the in-stent restenosis rate. So here we can see when the in-stent restenosis increase, the blood pressure also dramatically changes. So which means if we want to monitor the in-stent restenosis rate, we have to monitor the blood pressure. Thus, the MEMS-based LC wireless pressure sensor is selected due to its remuneration, wireless monitoring, passive and low profile. So here is some basic principle of the LC wireless pressure sensor. When we give some pressure sensor, the displacement will happen in the moving memories. So the sensor's frequency value will change. Use some outside network analyzer, we can detect the signal wirelessly. So based on this concept, actually our group have already proposed the polycraft polymer metal hybrid stent systems. Even though we have get a lot of achievements in this system, and we also conduct the animal tests in this system, but here is still a lot of limitations. So due to the lack of sensitivity, when we get the sensor data from the animal body, even though we can get some sensor data from animal body, but when we compare the sensor with the blood pressure waveform, we can see that our sensor's signal is not very clear, so we cannot get the valuable data. Based on this one, our target is to further increase the sensor sensitivity. So in order to increase the sensor sensitivity, our first thing is to identify the parameter that resists the diaphragm default. So based on the diaphragm displacement equation and our sensor structures, we identify that the primary parameter that resists our diaphragm deform is limitation of the cavity volume. Because when the diaphragm deform, the inside cavity volume will be compressed, which causes the inner pressure increase. So which means if we want to increase our sensor sensitivity, increase the cavity volume is a very efficient way. Thus, we just propose our sensors. So first, we just show our sensor structures. So here we can see actually the sensor's cavity volume is defined by the permanence layers. So when we focus on the whole design of the permanence, we only define the cavity volume on the flexible electrode area. So in order to create more cavity volume, we redesign the permanence layers to utilize the extra area. And in order to make sure the made deformations happen in the flexible electrode areas, we add some supporting pillar in the additional cavity. So here our motivation just we just creatively modify the design of the permanence layers to increase the cavity volume, then we can increase the sensitivities. So here is our fabrication process of our sensor. Our sensor is fabricated by two parts separately. In the inductor coil part, we use electroplating to form the inductor coil, which realizes the wireless transmission. In the diaphragm layers, we use our new design permanence layer to create more cavity volume. Then this two layer was bonded by thermal bonding process, so we can get the final product. Then we just evaluate the sensor's sensitivity performance based on the different cavity volume. So first we set our old design sensor cavity volume as 1 as a reference. So we further improve the cavity volume from 1 time to 3.8 time and up to 6.1 time. So we can see when we apply same pressures to the sensors, the change of frequency is increased according to the increase of the cavity, which means our sensor sensitivity will be increased. Then we just test the basic performance of the sensor. So first we already introduced is the sensitivity related to the cavity volume. And then we just further test the sensor's diaphragm displacement by laser micrometer to confirm that our ultra-sensitivity sensor had a diaphragm has larger displacement. Then we also test the sensor's resolution and also the long-term stability. So next step, we just move our sensors into the pattern system. So the pattern system is actually a system that mimics the cardiovascular conditions. Here we just use a pump to mimic the heartbeat, and we have the commercial pressure sensor. We can real-time get the reference pressure value in the system. Then the sensor was put inside the system. We use the network analyzer to wirelessly get the sensor's frequency value. So when we compare the sensor's sensor's resonance frequency value and the pressure value from the commercial sensor, we can see the high overlap of these two data indicates that our sensor is still working well in the liquid conditions. Then we just use some 3D print mode to mimic the restenosis rate. Here we just use 40%, 50%, 60% to mimic the early stage of the restenosis. So we can see when the restenosis rate increases, the pressure inside this system is also increased, and accordingly the sensor's frequency values also decrease. So which means we can, according to the sensor's resonance frequency value, we can determine the pressure value in which we can determine the restenosis rate. And the next step, we are going to the in vivo test, but before that one, I want to show you a small video to show how we conduct this animal test. So we use artificial blood vessel to combine sensors so we can implant this one into the animal test. So artificial blood vessel is fabricated by the electrospinning process with some PDO, PCR and jobs, so we can implant it into animal test, animal's body. Then we just use the 3D printing process to print some PCR code on the surface of the artificial blood vessel to enhance the rigidity of the artificial blood vessels. And we choose the pig as our animal model. Then we use some basic blood pressure method to get the reference blood pressure in the pig body. So we can get this data and compare with the census data. So we just replace some native blood vessel of the pig with our artificial blood vessel, which combine our LC as well as pressure sensor. So in that case, when the blood flow goes through our artificial blood vessel, the sensor's frequency value will be changed. And we also use the network analyzer to real-time monitoring the sensor signals. So here we can see the sensor signal is changing according to the heartbeat. And here is some data from the animal test. So we can see we use some artificial blood vessel to replace the native blood vessel. So here first we just compare the sensor's performance with our new design ultra sensitivity sensor and the old one. So here we can see with the improved design, our ultra sensitivity sensor get much more clearly data even though there is no any filters. So which means we can get more valuable data. And then we also compare the sensor's frequency value and with the reference blood pressure value. So we can see the highly overlap of these two data indicates that our sensor's reference change is actually from the blood pressure change. So all of these experiments actually show the potential of our sensor for the practical applications. So for here is some small conclusion. We just optimize our sensors design to improve the sensitivity, and we just conduct the in vitro and in vivo tests to prove our sensor performance in the real condition. And also I want to say thank you to my professors and also my lab member and the collaborators for this work. And thank you for your attention. Hope you can enjoy this presentation. Thank you so much.
And we may get one quick question from the audience. So let me ask you a quick question for you. So what was the diameter of the artificial blood vessel, and do we have the similar size blood vessel in our body?
Yeah, of course. Actually, this time we use the diameter is around 3.5 millimeter to 4 millimeter, and actually this stent is not actually only used in our cardiovascular condition. Actually, there are a lot of area we can use the stent. So in our body, the diameter of the vessel we can use is from 3 millimeter to 10 millimeter. So actually, we can use this device in our human body.
Okay, thank you. With that, we like to conclude our medical MEMS session. And thank you for joining us today. And actually, organizing chair, Vice Dean has some